I'm going to take you on a tour on the SPIFFE spec and how it can help to solve secret zero, or what other people are calling the bottom turtle problem. The purpose of this talk is to guide you through the basics of the SPIFFE framework and showcase how it can help you solve the secret zero or bottom turtle problem. But let's start at the beginning. What does SPIFFE actually mean? SPIFFE stands for Secure Production Identity Framework for Everyone. It's an open source project designed to establish a standard for securely identifying and authenticating software services in a distributed and dynamic environment, such as cloud-native and microservices architectures. The project aims to provide a framework that allows different services to securely communicate and trust each other's identities without needing to rely on traditional networking-based security mechanisms. Joe Beda, who is one of the co-founders of Kubernetes, first proposed SPIFFE in 2016. At the time, Joe was still working at Google, and he refined the specification of the SPIFFE framework together with security experts from other organizations with the aim to have an interoperable framework for workload identity management. There is an actively maintained open source implementation of the SPIFFE framework, which is called Spire, and it's maintained by many different organizations. And we have seen public use cases of Spire being run in production by the likes of Uber, ByteDance, the company behind TikTok, and many others. And there are many blog posts out there that you can start reading about it, of like people actually running Spire in production for doing zero trust security. So what does SPIFFE solve? It's all fine and well that we know what SPIFFE stands for, but what problems and challenges we face can SPIFFE actually help us? The first use case, and the one I probably get the most excited about, is removing the need for API keys. Imagine a world where you no longer need to have long-lived API keys or tokens. You don't have to deal with securely storing them or having to find a way to retrieve them from your secret store, which most of the time when you need to connect to a secret store, you also need to have some kind of authentication token as well. One of the major hurdles of adoption for SPIFFE, though, will be to make your application SPIFFE aware. But there are already some great software SDKs out there in different programming languages that make it very easy to start implementing it in your applications. And if you can change the application, for example, a common example is databases, you can always opt to put a proxy in front of it that's SPIFFE aware. A second use case that I've seen where SPIFFE is really useful is to authenticate from one cloud to another cloud through SPIFFE. An example could be that I can write a file to an AWS S3 bucket while I'm at the Google Cloud instance, or even when I'm on-premise with a virtual machine. And a third common use case I have personally identified of like a really great use case for SPIFFE is to give like your CI/CD pipelines, each step in your CI/CD pipelines, a unique identity that can help with auditing of your software supply chain. And you would also be able to use your SPIFFE identity to authenticate to your signing provider that then can sign your release artifact, like your container images, your Java jars, as well as all the evidence you produce as part of your software supply chain, like SBOMs or software bills of materials. Implementing SPIFFE is a major step in your zero trust network security story by giving all of your workloads, applications, and machines a unique identity. This SPIFFE identity allows you to do explicit authorization between your workloads. By using your SPIFFE for authorization between workloads and services, you prevent that API keys can be shared between multiple applications without your knowledge. I have seen countless times that one API token gets shared between 10 different applications, making it impossible to track where a request is coming from. By using SPIFFE identities, it allows you to have an improved auditing system on your authorization layer, as you can explicitly log from which SPIFFE identity a request is coming from. On the previous slide, I talked about that you don't have to think anymore where to store your API keys or have a way to retrieve them. A SPIFFE identity, in most cases, will be automatically provided as part of the platform your applications are running on. A great example of this is Kubernetes. When your application runs on Kubernetes, the platform team can automatically provide a SPIFFE identity and inject that into your workload, This makes the lives easier of the application teams, as they can focus more on adding extra features to their applications, improving reliability, and security on other levels of their applications. One of the big challenges with long-lived secrets is that most cases a regular manual rotation is required to stay compliant with policies and controls you have in your enterprise. SPIFFE takes this all away, and it's even recommended to have short-lived SPIFFE identities of between 1 hour to up to a maximum of 24 hours that automatically gets rotated and renewed. I put a quote from Joe Beda, who is the co-creator of Kubernetes and SPIFFE's original author, and it summarizes exactly on the previous items we talked about. It's very important to deliver great usability experience to improve the rate of adoption. SPIFFE is also a solution that works everywhere, on-premise and in cloud, serverless and even in the mainframe. The advantages SPIFFE gives on observability and policy enforcement are unprecedented. We now have talked about what SPIFFE is and what the problems it can help solve. SPIFFE is an open framework with its specification published to GitHub for everyone to see, use, and implement if they want. And we're now getting into the depths, and you are going to discover how a workload can get a SPIFFE identity and what SPIFFE identity actually is. So, to be able to start before talking more about SPIFFE, I'm going to start with the current status quo that we have, where we have a traditional application that wants to communicate to each other, but has to retrieve a client ID from a secrets manager. In our use case, we have like our application B that's going to retrieve a client ID from the secrets manager, and then it's going to want to connect to application X, and it's going to send over that client ID to application X. Application X is going to validate that connection, but one of the major downsides is this connection is not secured with MTLS or encryption. Also, application X can only validate the client ID, not if application B is actually allowed to talk to me. You have hex based on IP allow listing, but that doesn't work in regular changing environments like clouds and cloud natives where IPs regularly change. So, to be able to solve this, we're going to start implementing SPIFFE. And the SPIFFE framework exists out of 5 distinct components, and each component has its own function. And we're going to go over one by one. And we're going to start with the SPIFFE ID. This is to a human comparable to our name and how we are called and how we are calling ourselves. The SPIFFE identity looks very similar to actually what a website URL would look like, and it exists out of the following. The standard scheme that identifies what follows is going to be an actual SPIFFE identity. The second part is a trust domain, and this is to identify distinct domains of trust. One enterprise can even have multiple trust domains. A common example is to have a trust domain for production, another one for development. But even in production, you can have multiple trust domains. For example, if you want to have a distinct trust domain per data center if you are running multiple data centers. In this example of our SPIFFE identity, our trust domain is called venafi.com. And the last part is the path, and that is how you can identify your workload in a unique way. Each workload should have its own unique path, and the path can be a unique UID that's randomly generated and doesn't have any meaning, or it can also have a more meaningful name, as this is the case for our example that I have put it on the screen here. And we can see our workload runs in data center 1 on node 10, and it's the web server for the front end. And that's how your workload can be identified quite easily. So if we now go again to like our application, we have removed our secrets manager from the slide, and what we're going to do is we're going to again initiate our connection from application B to application X, and we're going to send over our SPIFFE identity. Application X can now validate this connection based on the identity and even authorize this identity because like it knows exactly which workload is talking to it. With this, we now have solved the authorization and auditing problem. Application X knows that the connection is coming from application B based on its identity, but we have currently still some other things missing though. This is not yet a secure connection with MTLS, and also application X needs to rely on good faith that is actually coming from application B. And this is why we need a SPIFFE verifiable identity document or SFIT. This is comparable to our passports we carry around and how we can get verified at border control. A SPIFFE verifiable identity document, or SPIFFE SFIT in short, is a cryptographically signed identity document that can be used to verify the identity of a workload within a specific trust domain. It is a fundamental component of the SPIFFE framework, which aims to provide secure and standardized identification and authentication for services in distributed and dynamic environments. Examples are microservices architecture and cloud-native applications. Currently, JOT tokens and X509 certificates are supported as cryptographic key materials, which can cover a lot of use cases. And as stated before, the certificate should have a really short lifetime that in case of compromise, the exposure is very minimal. This is an example of an X509 certificate, and we can see in there that we have an X509 version 3 subject alternative name, and in there we have our URL scheme with the SPIFFE identity in it. Each X509 certificate should only have one SPIFFE identity to make it very easy to be able to do authorization. We also have an example of our JOT token with audiences and the validity of it that then again can be verified. So we're going back to our application that we had originally set out with our two distinct servers, but now we will use a proper X509 certificate with a SPIFFE SFIT. Again, we initiate the connection to AppX, and we send over our unique SPIFFE ID as a SPIFFE SFIT in X509. Application X authorizes and validates a connection based on the CA chain that it's aware of where that X509 certificate got being issued. And with this, we now have solved the authentication on top of the authorization and auditing problem. Our connection is now MTLS secure. Application X knows that the connection is coming from application B based on its identity, and it can also be verified through the CA chain. We are still missing some big things though, and one is how can my applications get their SPIFFE SFITs from a central system, and how can the identities be issued in a trustworthy way? And this is where the Workload API comes in. Like requesting our passport at the passport office, we need a way to get a SPIFFE verifiable identity document for each workload. And this is done through a standardized Workload API. The SPIFFE Workload API that preferably runs on a local socket, or at least only listens on local host of a node, as it's an unauthenticated API. This API is a way to retrieve SPIFFE SFITs, and it's responsible for the automatic renewal and rotation of our SPIFFE SFITs, as we want them to be short-lived. And again, to reiterate, it's quite common for them to be between 1 and 24 hours of a maximum lifetime. So that's why this Workload API is responsible for doing the automated rotation of it. The Workload API also allows you to create integrations for your different platforms that deliver SPIFFE SFITs directly to your application on a well-known location. If you don't have these integrations, it's up to the workload itself to retrieve that SPIFFE SFIT from the Workload API. Currently, there is already an existing implementation for Kubernetes, but imagine a life that wherever you run, your workload can have SPIFFE SFITs, no matter where you run, from AWS Lambda functions to on-premise VMs to even mainframes. The SPIFFE Workload API is also an unauthenticated API endpoint, and that's why it only should be running locally. It is also responsible for validating and attesting the different workloads that run on that node. And this happens out of band. Otherwise, we wouldn't really be solving the secret zero problem, but more later on attestation and verification, as it's a bit of a separate topic. So we now have extended our architecture a bit, and we have added the SPIFFE agent to each of our two servers that we're running on, with a Workload API that's running on a local socket and is only reachable from within the boundaries of my server. What we're going to do is my application B is going to request a SPIFFE SFIT from this Workload API. And in the background, it's going to validate that the workload is actually what it says it is. And then it's going to send back a signed X509 SPIFFE SFIT to my application. In the background, each of my applications are going to get the SPIFFE SFIT automatically through our platform integration. And from there on, we kind of do the same story over as in the previous example. We initiate the connection. We send over our SPIFFE fit. Application X, again, is going to validate this one through the CA chain. And like, we have now solved almost all of our problems. And kind of the only problem remaining is being able to attest and verify that we can issue X509 or JOT certificates through our Workload API. So we can get SPIFFE fits from a central place, but we also need to make sure that those workloads are who they say they are. Like, we cannot trust them without double checking this. The verification of workloads can be happening in band, as that would require an API key, and we wouldn't really solve the secret zero problem. Verification and attestation of workloads needs to happen out of band and asynchronous. Verification and attestation for SPIFFE fits happens at two levels. First, we need to trust the node, as that is where the Workload API is running on. And after we trust the node, we can start trusting the workloads running on those nodes. And to be able to build up that trust, we need to gather evidence of the environment that the nodes and workloads are running on. For nodes in cloud environments, this can be done through querying the instance metadata, like for example the AWS metadata API, and retrieving the facts about it. In on-premise systems, this can be done through the TPM that can be found on them, or like for example the VMware API or other environmental verifiable data. Once the node is verified, the workloads that are running on a node can also be verified. And this is again done by verifying the environment, and proof can be gathered from the example, for example, the Windows, Unix sockets, or when running in Kubernetes by gathering proof from the Kubernetes API. This might all be a bit hard to grasp, but hopefully with the next example, it will be a bit of a better understanding. So again, we have like upped our architecture a bit, and now we have added a SPIFFE server, which is also in control of our CA and runs the node attestation one. We also have like added next to our SPIFFE agent the workload attestation and the node attestations. And the first step that will happen is that when a SPIFFE agent on one of the nodes comes up, it will gather information of where it runs. In on-premise environments, this can again be done from its local TPM, or in cloud environments through the cloud metadata API, and it sent this proof of node back to the SPIFFE server. The central SPIFFE server will verify this proof of node, and if all correct, it will issue a SPIFFE fit for the node, and then send it back to the agent. So now, our machine, our server has a unique identity, in this case venafi.com/server1. And again, for our second server that comes up, we also have like now a unique identity. Now what we can do is, our application can again request this SFIT, and our SPIFFE agent is going to verify the workload, and it's then going to issue a certificate that it's going to get signed by the SPIFFE server CA. And it's going to send this back to my application, and again for all the workloads, and it's going to authenticate again between app B and app X, and it's going to send over this SPIFFE identity. And it's all secure now again. And like, this is how it's all built up, and we actually solve this like true secret zero problem, as it can really be used for zero trust networking. And it's very important, like your SPIFFE server is going to be like the central figure in all of this, that you keep this really secure and pay a lot of attention to this, because like that's where a lot of power comes in. Like that's where your CA is going to be at, and that's where your initial root of trust starts as well. The last part I'm going to talk about is SPIFFE Federation. SPIFFE Federation is probably worth a talk on its own, but we're going to briefly and very high level cover it. And SPIFFE Federation is important when you run multiple SPIFFE servers. A common scenario is to have a SPIFFE server per data center, but you still want to have trust between those two data centers for cross-communication between workloads in those two data centers. And each distinct SPIFFE server has a trust bundle endpoint. And this can kind of be compared to like your CA root chain that you distribute to all your servers. And it publishes all of its public keys of that specific SPIFFE server, and only the public keys of that one specific server. And when a SPIFFE server wants to federate and trust another SPIFFE server, they need to explicitly define that in their config, and based on the refresh timing set in the trust bundle, the SPIFFE server knows when to requery the trust bundle to get an updated one from the SPIFFE server it wants to federate on. And this will allow for rotation of CAs, because like in your trust bundle, when you rotate the CAs, you can temporarily have like 2 public keys in it so that you can do the whole rotation. The 3 most common use cases for federation is to segment environments with different levels of trust within the same company. For example, staging and production environments, or PCI and non-PCI environments. A second use case for SPIFFE Federation is between different companies. It is similar to the first one, as federation will happen between different SPIFFE deployments, but there might be a bit of a difference in how SPIFFE has been implemented between 2 organizations. And the third and final use case is to enable consumers that don't have SPIFFE set up yet, and people without it can fetch the trust bundle of my SPIFFE server and use that to authenticate the callers without having to commit to set up a full-blown SPIFFE deployment. Afterwards, each SPIFFE server is responsible for distributing the trust bundles to each workload so that a workload can verify the SPIFFE SFIT from another SPIFFE server. It was a bit of a high-level overview, and hopefully in the future we can go a bit deeper into this topic. But again, back to our application, and now we have like 2 SPIFFE servers, and each with their own trust domain. One is dc1.venafi.com, and the other one is dc2.venafi.com. And we first start by building up trust on a control plane level. They exchange trust bundles with each other, and after they have each defined in their config that they trust each other. And as part of the trust bundle, again, like you have the refresh token, so each SPIFFE server knows in how that the time that they need to requery those trust bundles to get like an updated one. The trust then gets distributed to the workloads. This makes the workloads aware of explicit trust that exists between the 2 trust domains. And now we can see again that each app is part of a different domain, a trust domain, but thanks to the trust bundle exchange, they will be able to communicate with each other. So in this case, like now our application B is part of the DC1, while application X is part of DC2 trust domain. So they're part of different trust domains, but because with the distribution of the trust bundles, they can start trusting each other. And for the rest, like it's almost the same as like they would be in the same trust domain, and you can verify the connection and accept it, and it's all MTLS again. Before ending this talk, I have one more quote from the head of security and CISO of Notable, that SPIFFE is a game changer and how it helps simplifying TLS distribution to hosts. And this is very important. Like you can really gain a lot of developer simplicity with like implementing SPIFFE and making this available as like a foundational identity. So we're going to end this talk with a small summary on what we have seen. So we have seen that SPIFFE provides foundational identity. It reduces the need for API key distribution. It gives us a short-lived identity that automatically gets renewed. All of the attestations happens out of band by querying the cloud metadata API, gathering evidence from TPMs, or like for the workloads from Windows or from Linux itself. It's really going to make the lives easier of developers. Like they don't need to query anymore from secret stores. Like the identity is there when the application comes up, and they can trust on that it's going to be there and start using that. And Spire is an open source implementation of SPIFFE. But besides Spire, we also start to see implementations in other software, like Citrem earlier talked about Istio Service Mesh. Like they use SPIFFE as like their foundational identity for their workloads. Cert Manager has a CSI SPIFFE driver. HashiCorp Console supports SPIFFE. Dapper and also the 3 major cloud providers, AWS, Google Cloud, and Azure, are doing quite a lot with SPIFFE and supporting SPIFFE to a certain extent. Again, if you're interested in figuring out more about the SPIFFE spec and the SPIFFE framework spec, it can be found on GitHub, and you can start reading it. Like it's all freely available, and yeah, it's really enlightening to read it.